Now that we've looked at how we could set up the basic structure of how we want our model inferred, let's take a look at some slightly more advanced features which we will implement using the Fluent API. In this demo, we'll look at how to set up composite keys, alternate keys, default values, computed columns, and how to use backing fields. Backing fields are not related to the Fluent API, but they may be highly relevant depending on the business requirements that we'll be implementing. We're now back inside Visual Studio. Let's start by taking a look at the Carved Rock database context. Remember that we discussed that all the things that we did with annotations could also have been done using the Fluent API. The code that we see here in the onModel creating method is an example of that. During the previous demo, we set up the item class so that it had a decimal with precision 22 and scale 2 as the SQL type for its price property. And we also set up its description property to have a max length of 255, which resulted in it being inferred as an nvarchar with length 255. The code that we see here does exactly that. The first line sets up the decimal type of the price column, and the next sets up the length of the description column of the items table. But as you can see, this bit of code has been commented out since we don't need to set it all up once again. Let's instead look at what else is going on with the item class. In the following line, we set up the price column of the items table to have a default value of 100. This means that every time a row is added to the items table, the price will default to being 100 unless something else is explicitly specified. And the next line refers to a new property on the items class called price after VAT, or price after value added tax. If we take a quick look at the item class, we can see that there's nothing special about this property except that it is decorated with the column attribute in order to name the corresponding column unit price after VAT, and the type name property to make sure if core creates it as a decimal with precision 22 and scale 2 on the database. If we go back to the database context, we can see that the default value for this property is set to be the unit price multiplied by 1.10, which corresponds to a VAT of 10%. Notice that we'll have to use the column name that is stored in the database and not the property name on the class, since this calculation will be executed on the database. This calculation could have easily been implemented directly in the C# class, but had we done so and wanted to change the rule, we would have to recompile the code, whereas having it specified in the database allows us to change it in a central location that will immediately affect all installations targeting that database. There are several other uses for calculated columns, so this is just a simple example of how to use this feature. We shall shortly see this in action, but first let's take a look at what has been set up for the customer class. First, let's take a look at this bit of code here. Now, as we've previously seen, the customer class already has a key property, the ID property, which is incremented each time a new row is added to the customers table. But we can also define a different type of key. For example, we could define a composite key based on the first and last name columns. This would mean that we could only have rows with unique combinations of those two columns in the table. That would mean that if we already had someone in the table with the first name John and the last name Doe, we could not add another John Doe. But we would of course still be able to add a single instance of Jane Doe or whichever other combination of first and last name that did not already exist in the database. So this is an example of a composite key, but perhaps not the best one, since it requires uniqueness on something that is not naturally unique. So we shall not keep it, but rather comment it out. But just keep in mind that this is how you would create a composite key. We can also see here that an alternate key has been defined for the customers table on the username column. An alternate key serves as a unique identifier in addition to the primary key. It requires each row in the customers table to have a unique value for username and means that the username column can be used as the target of a relationship, so it can be used to set up foreign key relations. Let's look at how if core sets this up for us in the database. First, we'll create a new migration by using the add migration command here in the package manager console to create a new migration called Fluent. Let's take a look at what if core has done for us. The first thing that we notice is that the unit price column in the items table is being altered, and we can see that it has a line here that sets up the default value to be the decimal value 100. This will make sure that the default value is applied to the items table once we update the database with this migration. Next, we can see that the unit price after VAT column is added, and as we would expect, it's set up to have the decimal type with a precision of 22 and a scale of 2. We can also see that there's a line here that says computed column SQL. This means that the values that we'll have in this column are computed values that follow the formula that we specified earlier. Lastly, we can see that we are adding a unique constraint to the username column of the customers table. This corresponds to the alternate key we defined for the customers entity, where we specified username as the alternate key. Now let's try to apply this to the database by typing in update database. We'll start by looking at the customers table. If we use the Server Explorer to open up the table definition for the table, we can see the create script that we can use to recreate this table. Here we can see that the unique constraint that was specified earlier is applied to the username column. Let's also look at the table definition for the items table. Here we can see the default value for the unit price column, which is 100, and we can also see our new column, unit price after VAT, which we can see is computed based on the formula unit price times 1.10. Before we look at if all of this works as expected, I promised that we would also talk about backing fields, so let's just quickly cover them first. If we go to the customer class and take a look at the username property, we can see that it has been modified somewhat. Instead of being a simple property with just a get and a set accessor, it now has a get accessor that returns a backing field called valid username, and the set accessor has been removed. Instead of the setter, the class now provides a method for setting the username called setUsername, where the backing field valid username is set, if the provided username lives up to a business rule that requires it to not contain certain characters. Normally F-Core would not allow this, and if we tried to create a migration it would fail with an error saying that username does not have a setter. But if we take another look at the Fluent definition in the CraftRock database context, we can see this line here that has been added, which we did not explain earlier. What this line of code does is that it tells F-Core that for the field username it should read the value from the backing field valid username and not from the property itself. Notice that if we had instead named the backing field username or something else that would allow F-Core to recognize the field as backing field for the username property, we would not have had to set this up in the data context. F-Core would simply by convention assume that this was the backing field and use it as such. Actually, there's quite a lot of the magic that happens in F-Core that is implemented using conventions. In fact, this is the case for many other areas of the .NET framework. But regardless of whether we use a backing field that is mapped by convention or one that we manually map, backing fields can be a very useful tool in cases where we want to implement business logic in our C# classes that we do not wish to affect the database. And as we may remember from looking at the migration file, this did not affect the setup of the database in any way, so our database works just as before in regards to the username column in the customers table, except of course that we added a unique constraint on that column. Speaking of that, let's try to add some data to the customers table and see that unique constraint in action. Let's head over to the Server Explorer and try that out. First we'll try to execute this statement, which will insert the customer John Doe with the username John Doe in the database. If we do a select now, we can see that the row was added as expected. If we try to add the exact same data again, we'll get an error saying violation of unique key constraint ak_customers_username. Cannot insert duplicate key in object dbo.customers. This is because of the alternate key that we defined on the username column. And the duplicate value that we are trying to insert is John Doe. If instead we change the username to John Doe 2, everything will work fine, which we can see by doing another select. Remember that we discussed setting up a composite key on first and last name. Had we done so, we would still be getting a unique constraint error and would have had to change either the first or last name. Now let's try to insert something in the items table to see how our computed and default values work in action. First let's try to execute this statement. This will insert an item called thing1 with a weight of 10 into the database. Notice that we do not specify the price since we want to use the default price of 100. If we now do a select on the items table, we can see that thing1 was added and that it was given a unit price of 100 as we had specified, and based on that, the unit price after VAT was calculated to be 110. If we now execute this statement, what we'll do is to insert an item called thing2 in the items table, which has a weight of 10 and a price of 125. If we now try to do a select, we can now also see thing2 with its price of 125 and a calculated price after VAT of 137.5. So as we can see, both our alternate key, our default value and our computed column work as they should. In the demo we saw how we can further change how our data model is inferred using F-Core's Fluent API. During the demo we focused on some topics that are somewhat more technical than the ones that we focused on during the attributes demo. But as we discussed and also saw an example of during the demo, we could have implemented the same things that we implemented using attributes, but instead using the Fluent API. We also looked at code that we can use to set up composite keys for our models and how alternative keys are defined. Whilst keys might be seen as something that belongs strictly in a relational database, they do have real-world implications since they define the uniqueness in the tables. So depending on which attributes we decide to base our keys on will make certain restrictions on the kind of variety our model can express, If, for example, we had a table containing types of roses and we used the petal color as our primary key, we would never be able to represent the variety of roses that exist unless we were very creative in our use of different colors. And in addition to that, we would also have chosen a property of the rose that is probably meaningless in terms of defining uniqueness. Therefore, when we make a choice between a random key such as an integer or a grid, or a specific attribute or set of attributes as keys, we are making choices that will impact how our real-world model will behave. We also looked at how to implement business logic in the database using default values and computed columns, and how to make sure that we were always able to save our data model objects in the database regardless of any business logic that might be implemented in the form of backing fields. In this module, we looked at mapping our data model using attributes and the EF-Core's Fluent API. An important takeaway from this module is that all the choices that we make for how we design our database and how we map things in EF-Core will have implications for how our model works when it is used in our real-world applications. Also remember that the database is probably the least flexible place that we can implement rules, so think long and hard before you set something in stone by implementing it as a rule in the database. I hope that you enjoyed this module. In the next one, we'll take a look at mapping special scenarios. Hi, and welcome to the Mapping Real-World Classes in EF-Core 6 course. My name is Torben Jensen, and in this module we'll look at some special mapping scenarios that might be of interest as we're working on our data model using Entity Framework Core 6. There are many aspects to mapping data with EF-Core, and there are several complexities that may arise as we map our classes. In this module we'll look into some topics that could become relevant as we navigate the challenges of setting up our data model mapping. Some of the features that we'll look at during this module are not used all that frequently, but understanding them not only enables us to use them, but also to understand how EF-Core uses them under the covers. An example of this is how EF-Core implements foreign keys for us using shadow properties, or how property bags are used to implement direct many-to-many relationships. We shall also look at how we can have fine-grained control over how our entities are mapped by using value conversions. And finally, something that might be especially interesting if you are following domain-driven design practices is the ability to map value types using owned entity types. But for now, let's kick things off with shadow properties. We'll kick things off by looking at shadow properties. Like any property that is defined in our .NET entity classes, shadow properties map to columns in our database tables. But unlike other properties, shadow properties are not defined in any entity class, but they are instead maintained purely in EF-Core's change tracker. Shadow properties can be used for scenarios where there is data in the database that for whatever reason should not be exposed on our mapped entity types. For example, take a look at this implementation of the order class, where we have a foreign key relationship that we have mapped using a navigation property, but we haven't added a corresponding customer ID property. In this case, EF-Core will create a shadow property for us to contain the customer ID. This shadow property will then be maintained in EF-Core's change tracker and will be mapped to the column in the orders table that defines the foreign key relationship. If we created our database based on code first migrations, like we've in fact done for these demos, EF-Core will automatically create a column for us in the orders table to define that relationship. In the example that we see here, EF-Core would add a column called customer ID to the table, and it would then be this column that the shadow property maps to. No matter how we've created the database, we'll later on have the option of directly mapping the column in our entity model by adding a property for it and setting up the necessary mapping for this. Another example where shadow properties are used is when we set up one of our tables to be temporal. In the code that we see here, the customers table is set up as a temporal table by calling the isTemporal method on the customer entity. In order for this to work, two hidden columns called period start and period end are added to the customers table. These two columns are not exposed on the customer entity, but are instead tracked as shadow properties on EF-Core's change tracker. We won't be covering temporal tables in this course, but if you'd like to know more, I suggest you go to my Pluralsight course on querying data in EF-Core and take a look at the module on temporal tables.